Picking up where I left off in the last video, I'm going to show you this stack material component in HAL. Quite simply, this is just a component that gives you a stack of parts that the robot will grab in order to place in any configuration that you set up. So essentially the feeding stack for your block wall. So I'm going to, like I did with the other one, go through what each of these components are, because sometimes the naming doesn't always make it quite obvious as to what it is. So the stack plane is essentially where that plane is located. And we could just, like we did before, create an XY plane and put it there. But that's going to make the stack occur at the origin, at the center. So often in cases like this, what we'll do is we'll construct a point given coordinate values. In this case, we're just going to make them up for now. Right, this allows us to, maybe not precisely, but to set a coordinate of this plane in space in relationship to the robot. So you can see how I'm moving that point. And if I do one more, obviously this isn't going to be 1500 millimeters in the air, but in our case, we've been stacking off of a table somewhere around 600 millimeters in the air. All right, so that sets an origin for the stack of materials. Now I can now use that as the stack plane value. Obviously it's not enough to set the component, but that allows us to interactively in some ways control wherever that point is. Right. When we used ours, it was kind of off to the side of the robot. So let's continue going down the list here, and I'll try to explain these as best as possible. So the part coordinate system is essentially the coordinate system that you're going to use to pick or place your parts, right? Now the reason why this is asking for a coordinate system is your parts don't necessarily have to be associated with the world. They could be at an odd angle or in a different spot. And the example that they use when I right click and do example file kind of shows this. All right, so when this loads up, you can see that it's using non-orthogonal blocks. Trying to figure out how they would actually stack those. Another story. And placing them in a curved surface or non-orthogonal wall. So they have to use a different coordinate system in order to get that done. So you don't have to think in the XY coordinate system or the world coordinate system. But in this case, we're using simple blocks. We're going to. So we're just telling it to use the world coordinate system or XY as the orientation of the planes. So next it's going to want to know where the pick, or where is the plane that the robot is going to grip from. So in this case, I said earlier in the other video that we're always dealing with top planes that are at the top of the surface. So I'm going to create a representation of our block. So I'm going to create, in this case, a center block with some controls. I know that it's 45. I'm probably going to get these wrong, but I'll fix them. So not 45. 45 by 90. I'm not going to get the numbers wrong. I'm going to get the orientation wrong, probably. By 150, I already got them wrong. Still put it in there. All right. The height of the block is actually 45. So let's put this. All right. So you'll see maybe here at the center there's a block. Because we're using a center block, it's actually too big. So we need to have these values, but I want these to be real world values, so I'm just going to put it in an expression here at the input of this. And the reason why I'm doing this, if you don't understand it, is because it's a center box. It uses these dimensions times 2. It's dimensioning out from the center of the box, so it's essentially doubling the dimensions, which is not what we want. So by putting an expression here, I'm getting a true world dimension of our block. one more. I know this is slow. So with our geometry set up, I'm going to quickly hide some of this geometry so we can watch what's going on. So I'm going to hide the tool, and I'm going to hide the preview of the robot. I'm going to zoom in, and I'll see that because it's a center box, it's actually creating the middle of that box, and it's sitting below the ground. So we actually want to move that up. So we're going to make a new plane. We can feed a plane for where this box is. So if I just feed it directly as it is, nothing changes. But if I move that plane up by a value of, in this case, half of the height, so I'm going to use my height driver and use my expression again, say divided by 2. I've now moved that block up in space. But what we want, this is good for a geometrical, for our part geometry here, for a representation of it, but it's not good for how we want to grab it, because we want to grab it at the top plane. So what we're going to want to do is actually repeat this. So I'm going to take an XY plane. I'm going to move it. So I'm taking this plane, I'm moving it in the Z, just like we did before, but this time the height of the block, and that will be our plane. When I select it, that's the top of the box. So what we've done is we've created our geometry and our gripper plane. If you look at here, the part grip coordinate system. So we know that we want it to grab it at that point all the time, right? We also know, and that's essentially our plane. So we've just moved the XY up the height of the block. And we know that this is our part geometry. So we're going to feed that as the geometry for all of the parts. And the rest now start to dictate how the pile gets, or the stack gets created. So in this case, we're asking for a number of parts. So we're going to start small right now. So I'm going to put 4. All right, and then we can start to just copy this, and we'll see when we're playing with it what this does. So we have maximum parts in a pile. That's essentially the height. We have the number of rows, so we get to control columns and rows and heights. So we need part width, length, and height. Essentially, this is getting a bounding box, but because we are using a box, we already have all of these, so we can feed our same values here: width, length, height. All right, and the spacing is the spacing between the blocks. So we found that somewhere around 80 is ideal, clears the grippers, and I can feed that in there. So now I should have, as I do here, a representation of the stack. Let me turn the robot back on so you can see it in reference to that. Right. So what we've done is we've created a point, which is the origin, and it goes this way and this way, so it goes positive X, positive Y, and you can see as we increase the number of parts, they'll stack up. Let's get a good look at it. We increase parts in a row or decrease it, and the number in a pile. Meaning, I can go more piles. So if I get less in a pile, we start to go back the other way because it exceeds the row. But you can see how we can start to control the number of these blocks. So that gives us a stack on where it can grab it. And then having this point allows us to reorient the stack wherever we need to orient it. So it gives us some control because we don't have exact environments. Usually we get this coordinate from the robot. We'll move the robot to a spot in space, get those coordinates and feed it here, and that will give us the numbers for this. So what we have here for outputs is the gripping plane, which is the top of it, and so that's the top of each part. So it'll list all 10 of them and where that plane is located. We have geometry of each part, and we have the planes of the creation of those parts, which is what we did here. So we've got access to several different outputs that we can then use. Usually we take the gripping plane and we feed that into the next component that I'll cover in the next video, which is the pick and place component. But for now, it's pretty simple on how to create the stack. It looks a lot more complicated than it really is when you break it down.